What's up, Sarah? Video number 4, gonna attack the rest of that newer stuff, all the wave stuff, Rydberg equation, all that things that you're gonna be tested on Friday. I'm not sure if you're gonna be taking this test. Let me know what your scheduling is like. Let me know if you're still backed up. Let me know all that good stuff. So we'll get through the rest of those slides. We did one yesterday. Touch on them real quick. This is the packet 1018, 1019 learning objectives. Okay, page 214 to 226. Go through these pretty quickly. Not too quickly, but just bottom line a whole bunch of stuff so you're not sitting here watching this thing for like 3 hours and you're like, oh my God, I want to kill myself. All right, so here we go. First one, you have to memorize prefixes, okay? Prefixes, because when we're talking about wavelength, it's super small. Can't talk about meters or like even millimeters anymore. It's way smaller than that. So prefixes matter. Here we go. You can even see on your sheet. Got nanometers, micrometers, millimeters, centimeters, meters, and kilometers. Those are the main ones. So I'm going to write these down. And that's about it. So check this out. Got them written down, got them with the symbols, and got them with the exponents, okay? Kilo could be kilogram, could be kilometer. It means 1,000 of them, okay? I don't know why it's out of focus. There we go. Kilometers, 10 to the third means 1,000 because 10 to the third is 1,000. Then regular, like the base unit, just meters, just grams, just liters, could be whatever. 10 to the 0 means one of them, okay? Centimeters are the next most common used. 10 to the negative second. That means there's 10 to the second centimeters in 1 meter, or 1 meter is 10 to the negative, 10 to the negative second meters is 1 centimeter. Okay? Millimeters, milligrams, milliliters, whatever, 10 to the negative third. Micrometers or micrometers, however you pronounce it, you yourself pronounce it, 10 to the negative sixth. Picometers, 10 to the negative ninth. And then angstroms are special, 10 to the negative 10th. And you can see all the symbols there, cm, km, double M. Greek M for micrometers. That's how you distinguish between millimeters and micrometers. Micrometers have the Greek mu, which is the M in the Greek language. Picometers is PM, and angstrom is like a capital A with a circle on top. Those you want to know, you want to memorize them, okay? Next up, we got wave characteristics of light. As you know from last year, Greek letter lambda, okay, is L, length, wavelength. This is wavelength right here. And frequency is the Greek V shape. I honestly forget which letter that is, but I think it's like the lowercase phi or something because it's F. But it looks like a V. But rather than write a V like this, like for velocity, I do it a little bit differently. It's, you just kind of cursivize it, give it a little bit of a curl to it so it doesn't look like an actual V. But if you're cool with it as a V, you know its frequency, all good, because that goes as part of the equation. This velocity equals wavelength times frequency, or speed of light, which is a velocity itself, equals wavelength times frequency. Cool? And that's all from last year. That's all from physics. So a lot of those are basically plug and chug. You just got to know the units of all these things. Meters per second is velocity. Meters per cycle is wavelength, usually just meters. And then cycles per second, and then remember from yesterday's video, the cycles will cancel out, so you get left with meters per second. Cycles per second is known as hertz. So meters per second, meters, and hertz are the units you want to be cool with for this equation. A lot of it's plug and chug. Gotta watch out for sig figs and all that good stuff. So I'm going to pause the video right now. I'm not good at editing yet, but I'm going to get there. So then we'll go to slide 2 after that. Okay, we're back at it. One thing I want to mention too is that based on this equation right here, and this is true of any equation, okay, if you have one variable equals the product of two others, that means these two guys that are multiplied together are inversely proportional. One goes up, the other goes down. One goes down, the other goes up, okay? So if you have a big wavelength, that must mean you got a small frequency. So like radio waves, if you've seen the electromagnetic spectrum, radio waves, they look like this. They're like, you know, like I told someone one time, they're like the cartoons. They're like the Tom and Jerry. You know, Tom's a big cat, and he's kind of like goofy and clumsy, but he's big, right? So those guys on the left end of the, like, honestly, doesn't, I've seen them go both ways. If like the infrared's on the left and the other stuff's on the right. But like the ultraviolet and all that stuff. But anyway, whichever side has infrared and the radio waves, okay, those and the microwaves, those are the ones that have the huge wavelengths, but they're kind of clumsy. Okay, like here we go, here we go, here we go. Very big wavelength, very slow, very low frequency. Okay, one's high, one's low. On the other side, we have the dangerous stuff. Ultraviolet rays, X-rays, gamma rays, okay? Those are very, very tiny like this. Almost like Jerry, the mouse. He was very, very tiny, but he was very, very quick, very dangerous to Tom, okay? So, very, very, very tiny wavelengths, very, very, very tiny amplitudes, extremely high frequency, and that's what makes them dangerous, okay? So just keep that in mind. You cannot have a big wave and it move fast, or a small wave and it moves slow. Keep that in mind. Now, next up, we got the Planck-Einstein equation. Okay, and on your sheet, it tells you how Max Planck solved the problem of temperature of a substance and intensity and wavelength of the radiation emitted. Max Planck said that the problem could be solved by assuming that energy can be released or absorbed by atoms in discrete chunks of some minimum size. And what that means is there's only certain amounts of energy that can be released by an electron. Okay, that's basically what's going on. When an electron, which is on the outside, the outer realms of the atom, it's orbiting, quote unquote, that's what Bohr thought, the nucleus, right? But it's really a probability density function, which we'll see later. It can get excited because when radiation comes to an atom, what gets hit first? The electron or the nucleus? Okay, the electron, because it's further outside the nucleus. It's like if a meteor encounters the Earth, what gets hit first? The Earth itself or the atmosphere? The atmosphere, that's kind of like where the electrons are. So when that electron or those electrons get hit with this radiation, they get excited. They take it all in and they jump up further away from the nucleus into physically denotated areas, okay? We say that energy is quantized, okay? That's why it's called quantum mechanics. And it says here, Planck called this minimum amount of energy absorbed or released a quantum because it's like a whole number amount of energy that's absorbed or released, okay? So once the energy is absorbed by an electron, it jumps up to a fixed distance away from the nucleus. And then eventually it settles down and drops back down. when it drops back down to its normal position in relation to the nucleus, it releases the energy that it took on first to jump up further away from it. And that is called a photon. The way I describe it is it's like the electron sweats out light. When we run, we exert ourselves physically, we sweat, like liquid, right? Electrons sweat light. And that light that they sweat is called a photon. And the energy of a photon is based off this Planck-Einstein equation, which is E, the energy of a photon, equals Planck's constant times the frequency. Boom, that's what it's about. Okay? And this constant right here has a very defined value, 6.626 times 10 to the negative 34th joule seconds. Okay? Interesting. Here we go. Okay? So, the practice on the bottom of your page right here, it says a laser, and hopefully you have the page in front of you here so you can just follow along and I'm not just like talking randomly. Okay, a laser light emits, just kidding, a laser emits light that has a frequency of it says 4.69 times 10 to the 14th seconds to the negative first. A very interesting way of describing hertz, but it means like divided by seconds. So I could put this divided by seconds, which really implies it's cycles divided by seconds, like cycles per second, which is another name for hertz. Okay, so don't get confused by that. I'm not saying you are, but if you are, it just means hertz. Because you know its frequency, it's got to have hertz as its unit. Okay, so no matter how it looks, if it looks like that, just say I'm just trying to be crafty, let's say. It's hertz. So, you're asked about what is the energy of one photon? So energy equals, I don't know. All right, I got this equation. I'm solving for energy. That means I better have H and frequency. I got frequency. I got H. It's a constant. You're just going to multiply those together. Okay? So I'm going to multiply a 10 to the negative 34th times a 10 to the 14th. So when you do that, you're going to move the decimal maybe one way or the other. And what you end up with is the following. I'm going to leave the units out of it just so I can get the numbers down. Okay, that's what we got. When we do the work, that's what we end up with. 3.11 times 10 to the negative 19th joules, straight up plug and shove. Sound good? Now, number 2 says, and I erased that. Okay, if you need it, go back, scroll the video back a little bit, you'll get it. But be sure you write it down. All right, if the laser in this previous problem emits a pulse containing 5 times 10 to the 17th photons of this radiation, what is the total energy of it? Well, I know that 1 photon is that much energy. So 5 times 10 to the 17th photons would have 5 times 10 to the 17th this much energy. So all I do is I multiply that times 5.0 times 10 to the 17th. And that result is a lot bigger than before because I'm multiplying it basically by like 5 quintillion or something like that. So it's almost a full joule of energy. It was 10 to the negative 19th for a single photon, but if you have like a junk load of photons, you're going to have a junk load more energy. And 10 to the negative first is a heck of a lot bigger than 10 to the negative 19th. Okay? So that's problem 2. Problem 3 says, if the laser in problem number 1 emits 1.3 times 10 to the negative 2nd joules of energy during a pulse, how many photons are emitted? Now that's interesting. So I know that one photon from that first problem has this much, 3.11 times 10 to the negative 19th joules. Okay. But now it's saying this laser goes all the way to 10 to the negative second. Well, we know that 5 quintillion, or whatever this number is right here, produced 10 to the negative first joules. But now the laser is producing 10 to the negative second, so almost as much. So we want a huge number because of that. How do we get that huge number? We say, okay, it emits 1.3 times 10 to the negative second joules. Okay, yet one single photon was really, really tiny. It was, where is it? 3.11 times 10 to the negative 19th joules. So all you do is you say, I'm going to divide them. That's all you do, okay? And whatever you get when you divide these is your answer. Again, you want a big, huge number, and this is the way you get a huge number. You're just comparing the value of how many photons there are to the value of one single photon. It's basically like saying, hey, one bagel costs $3, okay? How many bagels would you have if you're paying this much more? You'd have to divide. So like if one bagel costs $3 and you're spending $300, how would you find how many bagels that is? And say, oh, 300 divided by 3 is 100. Oh, so I'm buying 100 bagels. Same concept, just with weirder stuff and with stupid scientific notation, unfortunately. Okay? And the last one says calculate the energy of one photon of yellow light that has a wavelength of 589 nanometers. Well, that's a unique problem. It doesn't have anything to do really with the first three. It's just this formula, but you are asked for the energy of it. Okay? We need to use this formula because we're given the wavelength, and that's all we're given. Okay? Yet the equation for energy is really this. That looks like an R, but it's really the frequency V. Okay? We're looking for energy. We're only given wavelength. So we have to solve this equation here for wavelength like so. So once we find 3.0 times 10 to the 8th, this thing keeps unfocusing, and I don't know why. Come on, buddy. Work with me. There we go. So once we find 3 times 10 to the 8th and we divide it by our wavelength. No, we were given wavelength. I'm sorry, we don't. Well, I can't delete the whole video now. It's 6 a.m. where I am. I'm a little tired. Sorry. If we divide both sides by wavelength, we solve for our frequency. Okay? We do 3 times 10 to the 8th divided by the value they give us, which is 589 nanometers. Okay? Now, I don't need to do scientific notation for that bottom number. I can just, if it's nanometers, I can just say 589 times 10 to the negative 9th, and I'm good to go with that. So then once that happens, you get a huge number, and then you plug it right in there. You take this number, you plug it in right there, because you already have that, because that's Planck's constant, which is a 6.626 times 10 to the negative 34th number. You multiply it by that value, and you end up with your energy. So that's a two-step problem, okay? When your teacher asks you something like that, your teacher is wondering, will Sarah know that she needs not only the C equals lambda frequency equation, but she also needs the E equals H frequency equation, because she's asked about energy, and I'm only going to give her wavelength, which is not part of the E equals H times frequency equation. Okay? Is she going to know that if I give her wavelength and I ask for this, she's going to know how to bring this into the mix. And if you know that, that's very, very good. So just know, you're going to have some times where it's not just a basic, quote unquote, plug and chug. You're going to have to get a little bit creative. And what I tell people is, hey, if you're solving for energy, I wonder what equation you're going to use. Then try to see if it's a one-step process. Is it a one-step process? Well, I know that. That's the Planck's constant. I don't know that yet. Yet they give me wavelength. I wonder if there's an equation that relates frequency and wavelength. And there is. Just use it. Okay? Pausing. Going to go back to sheet 3 in just a second. Okay. Slide 3 is about Rydberg's equation. It says Swedish physicist Johan Rydberg developed an equation to calculate the wavelengths of all the spectral lines of hydrogen. Now, what spectral lines are, when the electrons in hydrogen, how many electrons, by the way, are there in hydrogen? So when the electron in hydrogen goes up in energy level because it absorbs energy, and then it goes down in energy level, or maybe it jumps up 3 and kind of eases its way down. Maybe it jumps from the first energy level to the 4th energy level, then goes to the 3rd, then to the 1st. Each time it drops down and gets closer to its home, closest to the nucleus, it's going to release, like we said before, a photon. But depending on its wavelength, it may be a different color. So that's what you see on your sheet there. Okay? And the formula itself is basically a plug and chug. Okay, that's all it is. It looks weird because there's a lot of fractions in it. It's 1 over wavelength equals Rydberg's constant times 1 over the first energy level minus squared minus 1 over the second energy level squared. And yeah, so it's kind of interesting. And it's also very easy. It can be made very complicated, like I think your teacher tried to do, because she uses like -1 power again, rather than saying, okay, let's just plug and chug it in and then flip it at the end. So if you're not sure what that means, I'll show you. So practice using Rydberg's equation says, find the wavelength of the spectral line. And that's a key. Spectral line, you want to use Rydberg's equation, okay? Because she's not going to say, hey, use Rydberg's equation to solve for the wavelength of a spectral line. So keep that in mind. Find the wavelength of the spectral line produced when an electron falls from energy level 6, like 6 levels away from where it should be in relation to the nucleus, back down to energy level 1. So Rydberg's equation again is this. So here's what she did. She said, let me focus this. Okay, 1 over wavelength equals Rydberg's constant times 1 over n1 squared, the first energy level squared, that's what that means, minus 1 over the second energy level, n2, also squared. So it's got a subscript and a superscript. That's confusing in itself. And it happens twice. That's confusing in itself. So then what she says is, okay, I'm going to plug in the decimal for this. I'm not going to say per meter. I'm going to say meters to the -1, which means per meter. So like this much stuff per meter, and then that. But that's not enough for what she does, okay? She's going to say, no, I don't want to solve for 1 over wavelength. I just want to solve for wavelength. So what she does is, she says then, okay, wavelength equals all that to the -1 power. Okay, all she did is she said, okay, I'm going to flip this fraction to get lambda over 1, which is just lambda. And then that means I got to flip this thing, which means I put 1 over it. So all this stuff would have like a 1 on top. And that would be confusing because then it's fractions within fractions, because you'd have this right here would be the denominator of a big fraction with 1 on top, which is called a complex fraction. So rather than do that, she just says, okay, I'm going to make all this stuff to the negative 1 power. Honestly, I don't like doing that. That's not what I'm going to do because I don't like negative exponents. I'd rather have fractions and fractions instead of negative 1 powers, but you can do it either way, honestly. Now, the key is what goes where. I keep saying, hey, it's a plug and chug. It's just a plug and chug. Don't worry, it's just a plug and chug. So where do I plug and chug? What do I do? Okay, it says find the wavelength of the spectral line produced when an electron falls from energy level 6 to energy level 1. So that means that the 6 goes here or here, and then I square it, or, you know, and the 1 goes here or here. So one of these guys is 6 squared, and one of these guys is 1 squared. So it's either 1 over 6 squared minus 1 over 1 squared, or it's 1 over 1 squared minus 1 over 6 squared. The question is, how do I know which one goes where? Where does the 6 go? Where does the 1 go? Does it mean like the first one is where it starts, and the second one's where it ends? Or is the first one where it ends and the second one where it's... I don't know. The key is this. You don't worry about anything else except for this. Okay? When you're doing this, when you're plugging in, remember, you're solving for wavelength. It's a length. And remember from geometry last year that lengths can't be negative. Okay? They can only be positive. So whatever you're subtracting, you want this part of the formula here, this fraction minus this fraction, you want it to be positive. So if I say this is 6 and that is 1, I would get 1/36, because remember I'm squaring my denominators. 1 over 6 squared is 1/36 minus 1 over 1. Does that sound like a positive number or a negative number? I would say that's a negative number because 1/36 minus 1 is like negative. Huge. So this has to be the 1, that has to be 6, because then you're doing 1 minus something smaller than 1, which stays positive, which is what we want. So here's what I'm going to say. Okay? Remember, this is just 1 over 1 squared, and this is 1 over 6 squared. So then I could say this is just 36/36, which is 1, minus 1/36, so I get 35 over 36. Okay? And then I'm going to multiply that, and whatever I get is going to be 1 over wavelength. So let's just say, you know, this is 35/36 of that. So this is very, very close to 1. So I'm going to just make up my own number because I'm using my phone. I'm using my phone to record the video. Calculator's on my phone. And I don't want to pause the video and do it. So I'm just going to make it up. But you can use your calculator to do this number times that number. And I'm going to say, for example, just to show you how to do it, that 1 over wavelength equals 1.08 times 10 to the 7th. Okay? So then if I want to solve this thing really quickly, now I'm going to physically flip both sides. So I'm going to say that lambda over 1 is just 1 over that. And then I pop that into the calculator. Whatever that is going to be my wavelength. Now your teacher might also say, would it be visible? Well, I don't know. You need to know the wavelength of red light, which, if I remember correctly, was like 420. It's around 400. And purple is around 700, both in nanometers. So let's say you get like 47 nanometers. It's not between 400 and 700, or like 380 and 6, whatever. So you'll look in your book and find out what those values are. The wavelength of red visible light and the wavelength of violet visible light. As long as you're between there, it's visible. If you're not, it's not. So if you get like 514 when you do this, then yeah, it's going to be visible. Okay? But remember, we're going to be talking about nanometers now. So you're going to have to get something times 10 to the negative ninth. So if you get like, for example, again, let's say you get let's just say this is the answer, right? 10 to the negative 7th is not a nanometer because it's not 10 to the negative ninth. Okay? So what I would have to do is move this decimal 2 places to the right, and that means because this part of the scientific notation number got bigger, this exponent has to get smaller. So I need this smaller by 2. I need to move this decimal bigger by 2. So I would get 107.2 nanometers, because remember, 10 to the negative ninth means nano. So, would you say that 107.2, and again, these numbers are not accurate, I just made them up to illustrate the point of how to do it, okay? Would you say that 107.2 is between roughly 400 and roughly 700? No. So therefore, it's probably not in the visible, it's definitely not in the visible range. I don't know why I said probably. It's not. Okay, I'm about to pass out. I'm exhausted. I'll do the next 2 sheets of this packet tomorrow. Okay? So give me some feedback. Let me know if you find this helpful. And until next time, peace. Hope you're feeling better.